Okay, good morning. Last time, remember I said electric generator and electric motors are actually the same thing, right? So do you believe me or not?
Yes.
Okay, I have a proof here. This one, I will give you this pass. You can take a look. This one, you can see the label says this is a step motor. This one is from a very old printer. So you input the electric signal, then this one will step drive, so you can print something. So this is step motor for the printer. And we get this now. Instead, we apply electric current source, and we just connect to a load. In this case, it's LED. Now we mechanically drive this one, so you can see we can create electric power, so to light up the LED. If you apply the power here, then this one will drive. So this is the motor. Then if you turn this, we have electricity generated. So this is a generator. So you can see it's no difference. Right? Depends on what's your input, what is your output. Okay, you can take a look at it. Right? Today we are going to discuss the new chapter called the AC circuit, AC voltage basic AC current. We discussed so far the source, no matter voltage source, current source, have only one direction. That means, for example, if the voltage source, if we have like this, the current only flows in this direction. Never change the direction. The current can only flow this way, not flowing in back this way. So that is called a direct current. We call it, or put this simple as DC. And today we are going to discuss AC, alternate current. Alternate current means the current can go positive and negative, can go both ways. Anyone has taken trigonometry? Right now, okay. So I assume everybody knows the sine function.
Yeah.
Right? Sine function. How does the sine function look like?
Like that.
Like this, right? Yeah. This is sine function or cosine function? Sine function. Okay, cosine function when t equals 0 equals 1, right? Okay. The sinusoidal waveform is called sine wave, and that is in circuit we call sine wave, or in physics. In math we call sine function. Is the fundamental alternating current AC and alternating voltage waveform. And how to represent this waveform? You know trigonometry, so how to represent the waveform?
To represent the what?
Represent this waveform, this wave right here, this function, right? In math, how to represent this function? Sine times sine t, right? That's a function of t. And here we have this one is the maximum voltage or maximum current, depending on what we have here. Right? If this is voltage, then that is the maximum voltage. This is the maximum positive voltage. And this one is the maximum negative voltage. And 0 is here, 0 is here, 0 is here. Right? Electrical sine waves are named for mathematical function with the same shape. And what is wave? We may know this. We have a pond here. If you throw a stone inside, then we are going to have water will propagate from the center and all the way to the outside, all the way to the back. Right? So if you look at this, you can see these are the shapes of a sine wave or cosine waves. Right? And in this situation, you can see the waves oscillating like a sine wave or cosine wave. But in electricity, even the current or voltage are sine waves, we cannot see that. Right? Although we can watch this with some equipment, for example, oscilloscope, but we cannot see this directly with our naked eye. Sine wave, we know, is a periodic function. And all periodic waves can be constructed from sine waves. Periodic waves. What is a periodic function?
It has a period type.
Okay, has a period like, for example, sine wave is 1. Any other periodic functions you may know. Sine function is 1, cosine function is another. Trigonometry is like a tangent, cotangent. What else?
Tangent, cosecant,
For example, if we have this one, 1, 0, 1, 0, 1, 0, like this. So high, low, or the switch as on, off. So we say this 1, this 0, this 1, this 0. Is this periodic also? We do have a period like this, right? So from here to here, this is the period. So we repeat itself in time. So this is called the periodic function. So theoretically, any periodic function, maybe like this, right? Period, right? Any periodic function can be constructed with a lot of sine or cosine functions. We have theory for this, and later time in signals and systems, Fourier transform or something, you are going to learn how to represent any periodic signals with sine or cosine waves. But here, you only need to know any periodic functions can be represented by sine cosine waves. So that's why sine or cosine waves are very important. So this is very important. So here, this is a typical sine wave, and it looks like this is for voltage, right? You can see from the y-axis, that is voltage. And we have the maximum, it's called peak value. The peak value equals, what is it? 20, right? 20 volts. And we have a negative peak, it's negative 20. Usually they are symmetrical, one is positive, another one is negative. And we have one period is from here to here. It's obvious if this wave will repeat itself in another cycle, another cycle. So this is called the period. In this example, the x-axis is time. So what is the period? How large is the period? That means
50 microseconds.
in microsecond. So what is the value? 50, right? 50. Okay, 50 microsecond means each 50 microsecond, this signal will repeat itself. If you draw this, then another one, up to this point, it will be 100. Then another one is 150. The amplitude, the maximum value we call this amplitude, A of the sine wave is, we know that's 20. And the period is, we already know that, it's 50 microsecond. The sine waves, the period of the sine wave can be measured between any two corresponding points on the waveform. For example, if I give you this, I let you measure the period. How are you going to measure this? You can measure, for example, from here to here, right? This length. Or you can see from this top to that top, this corresponding point. Or can you measure from this to here? No, this is not, because this point does not correspond to this point, right? Because this point is up, this one is down. So this point and this one does not correspond to each other. Instead, this one and this one are the same. So this one is up, this one is up. So you can measure the distance from here to here, or from here to here, or even this one from in the middle, or to here in the middle. So you can imagine. So any pairs of corresponding point can be used to measure the period. Right? So that is easy to understand. So here, this one, or this one, or this one, or this one. So later time, when we study AC circuit in ECET101, you will need to go to the lab to measure the period for a given AC waveform. Right? Usually, it will labeled on the top, tell you what the period is. Or if you want to measure by yourself, you can see there are some like marks you can read from between corresponding 2 points. The difference between that 2 points is called the period. So you can measure by yourself. Right? This also. Then, if you want to measure the amplitude can only be on the peak value. Right? So this is A, that is good. If you measure any other point, it's not correct. So that is maximum. Right? Frequency. What is the frequency? Frequency is a concept that is called the number of cycles that the sine wave completes in 1 second. That means how many times it repeats itself in 1 second. Right? The unit for the frequency is called hertz, or cycles per second. Okay, now let's go back to this one. What is the frequency of this signal? The frequency is how many cycles in each second.
It is 1 complete cycle.
Right? In 1 complete cycle in how long? 50 microseconds, right? We need to count how many complete cycles in each second.
50 microseconds.
So the period is 50 microseconds. So how many cycles in each second?
1.
In each second.
2.
It's going to be big.
Yeah, I think it's a large number. 1 second.
1 second. How many microseconds in each second? A lot. Yes, a lot. How a lot?
1 million.
10 to the 6.
1 million.
Okay, 1 million, right? 10 to the 6. So that is how many microseconds in each second. So for each 50, we have 1 cycle.
1 million.
So 1 million divided by 50, right? Does that make sense?
Yes.
Everybody?
Yes.
So 1 million divided by 50 equals, what is it?
20,000.
20,000
hertz.
So that means in each second, this one is 50 microseconds, that 1 second is very far away, right?
Yeah.
So you count how many cycles, 1, 2, all the way up to 1 second, then you are going to count like 20,000 times. So the frequency is 20,000. What is the unit? Hertz, okay? 20K hertz. That is the frequency.
It's H times
Does it make sense to everybody? Okay, now we can imagine if we know the period T, the T in this example equals 50 microseconds, and we want to know the frequency F, how to get that? What's the relationship between the frequency and the period? How we get 20K in this example? You use 1 minus the T, right? Sorry, 1 divided by the T. Mistake. So 1 divided by the T, right? Yes, so that is the correct formula. So the frequency, use F, is related to the period by 1 over T. If I give you the frequency, how to find the T? Right? Then T will be equals 1 over F, right? Same thing, right? Anyway, F times T equals 1.
Wow.
Right? And this is very simple to discuss here, right?
like a lot.
Right? Yes or no? Good?
Yeah.
Alright. I just want to make sure. Okay? Example, if 3 cycles a wave occurs in 1 second, right? 1 cycle, 2 cycles, 3 cycles, and in 1 second, what is the frequency? 3 hertz, right? Hz, right? Capital H, little z.
Refresh rate.
So 3 hertz.
3 hertz refresh rate.
Why 3.0?
Terrible.
Why is it 3.0 instead of 3?
Because the
1.0 second.
Okay, because of the 1.0, right? This is called a significant digit.
Buy a console.
Cool.
Those are the formulas. F equals 1 over T and T equals 1 over F. In your calculator, you may have this reciprocal function. It's easy to calculate this. And now we already know that. Right? So the period equals 50 microseconds, and the frequency equals 0.02 megahertz, or equals 20 kilohertz. Okay, press. We need to memorize this unit. M, capital M, use capital M, right? Can you use small m?
No.
What does small m mean? Oh, small means million, 10 to the negative 3. Capital means 10 to the 6, okay? Megahertz. This H must be capital, right? This one must be small. K means 1000, right? 10 to the 3. You can use capital K, you can use small k. That looks like it doesn't matter, right? Alright. How to generate the sine wave? We use the thing that you just. Where's my device? Where's my? Clear with that? Okay. This thing is used. Can be used to generate. So this is the generator, right? This one can be used to generate sine wave. Right? You want to know what is inside, right? Okay, inside is that guy. On the left, we have a magnetic north pole, south pole like this. This is a schematic diagram. It's not the physical, not necessarily like this, but we can use this one to explain. And north is that side, south is this side, so the magnetic field will be outside the magnet. It is from north to south, so you can see the arrowed line from left to right. And we have a loop. The loop will be just, for example, rectangle or square, usually like this. It didn't draw here, but anyway, it's for example, rectangle wires. That if I draw here, it will be like this, and these two terminals will the output terminal for signals. And this loop is like this. This loop can be any shape, but usually we use this rectangle for explanation. So this one will be like this. Now, if you let me get a piece of paper to represent that. Is mine here. Suppose this one is the loop, right? This one is here, and the two terminals are from here, like this. If I put the loop like this one here, and we know there's a wire here, there's wire here, there's wire here, and there are two separate wires here. Then I turn this. If this one, when this is parallel with the magnetic line, at this point, if I turn, at this time, this wire will cut the magnetic field line, right? And at this point, we are going to generate the maximum voltage, which is this point, right? And then we go up, turn clockwise here. In the middle, this voltage will drop. Okay, it will be dropped to this point. When this one is vertical, so that means at this time instant, this wire here will parallel with this magnetic field line. At this time, they are in parallel. So if I turn this at this time instant, very short, there will be no voltage induced or created or generated. So that will be this one, this point. Right? So you can see this is a half cycle. Right? Then you turn like this one, it will be negative, change the direction. So that's why it's called AC circuit sine wave. So this is a positive, this one will be negative. Right? Then like this, give us the maximum here, then go back to here, okay, give us 0 again. So that is how we generate it. Right? Any question on this? Later time, when you are senior, right? If you take ET 461, electric powers, we are going to discuss how to actually generate electric power, how to transmit, how to do all these things, the industrial electric generator is very big, right? And motors also. So here you only need to know the basic concept, how this works. When the conductor is moving parallel, there's A, parallel means at this point, right? Or at this point here, both parallel, right? So that's A. Then B means we have the maximum voltage, which is this point, and C, parallel again, so that will be 0. And D, the direction of this, and this will be opposite. So Y is positive, Y is negative. Right? That's how we generate sine wave voltage. And this one is more real. That is what just discussed. And these two terminals with the brushes will output the electric signal, or electric power, or electric voltage, or electric current, no matter what. Right? And those are the coils. Usually, I demonstrated here only one coil, but actually there are a lot. Theoretically, the more the better. Alright, so those are the structures for how to generate the AC alternate, AC source. So this is called the AC generator. This one you see here. You turn this, and the two terminals give us the voltage. So can you see it is
Flickering.
yeah, why it is flick? Can you explain this?
Because it's in between on and off.
Yeah, yes. Between the maximum
And
be
minimum.
0 and negative, but negative because both ways, so negative and positive both give us
Light.
light, right?
So there's
But
zero.
there's 0 here, so you can see why
Yeah.
it is like this, right? So everybody is, if you run very fast, then because in each second, if you have more than 24 frames, you cannot see the difference. So if you this very fast, you can see it steady, but actually it's not. It's still on off.
Just high.
Just very high frequency. Right? Does it make sense? That's good, right? Okay, here. And the small alternators may use a permanent magnet. I believe inside we use permanent magnet. But for big industrial, the ones, for example, you use at home to generate 5 kilowatt or something, they may have both permanent and a little bit electric magnet. But for industrial, they do not use permanent magnet because they need a very big magnet to produce the magnetic flux. Alright, so here is look at this. We have only one pair of poles, North Pole, South Pole. We have only one pair. And more real, in industrial, we need more pairs. For example, this example showed 2 pairs. What's the benefit for we have 2 pairs? In each revolution, which means in each complete turn, look at the waveform on the right. How many cycles do we have? We have 2 complete cycles, right? One is here, another one is here. This is only one revolution. That means you turn this from this way, then you turn all the way back to here. So only one complete revolution give us 2 complete cycles. But the most industrial, the real actual has more than 2 pairs. Actually, they use 3 pairs. So that's why sometimes it's called 3-phase. Anyone has worked with any motors or something?
Yeah.
So 3-phase motor, right? So why it's called 3-phase? 3-phase means we have 3 pairs of this. Each one is separated by, this one we have 2 pairs. They separated by 180 degrees, right? And 180 degrees. And if you have 3 pairs, each one will be separated by 120 degrees. Again, we are going to discuss the technical details later time. And here, if we have 3 pair or 6 poles in each cycle, in each complete revolution, we are going to have a 3 complete cycle. Right? Suppose I turn this in each second. I turn 1 revolution.
1/3.
Right? In 1 second, I turn this 1 complete revolution like this. What is the frequency here?
2/3.
2 hertz, right? 1 hertz. This is 1 second. So 2 hertz.
2 waves.
If we have 6 poles, the frequency will be
6 what?
3 hertz.
3 hertz. If we have 6 poles, so this we have 1, 2, 3, 4. If we have 6 poles, it means 3 pairs. In each revolution, if 1 second each one equals 1 revolution, then the frequency will be 3 hertz. Right? And anyone knows the power line here? What is the frequency for this power line? The AC you use to drive this light or something on the wall. Anyone knows that? 60 hertz. Right? That is 60 hertz. In some other countries, maybe 50 hertz, but usually there are only 2 types, 50 hertz and 60 hertz. In North America here, 60 hertz. Okay, suppose, now, make everybody think about it. If the frequency equals 60 hertz, I use 6 poles or 3 pairs. How fast I should turn this
6 poles.
6 poles? Yeah.
Okay.
So we have 6 poles means 3 pairs. 6 poles equals 3 pairs. And the hertz frequency equals 60 hertz. I want to know how fast, for example, in each second, per second,
20.
how many revolutions?
20 per second.
Is 20 is good? Right? Yes or no? So 20 times 3, right? Equals 60 hertz. Usually we do not see the revolution, we do not use this unit per second. Instead we use RPM. Anyone knows this before? Yeah. If you work for motors, if you want to buy one, it will rate it like how many RPM, revolution per minute. So this one, 20 revolutions per second equals, the RPM equals what?
20 per second.
1
times 60
times 60, right?
1200.
1200, yes. Right? So this RPM equals 1200 RPM. So revolution per minute. This one is 20 per second. Do you have this here? The RPM is a typical parameter for motors. For high-speed motors, when do you use a high-speed motor? Can you give me an example? In your daily life, you don't work for your home, right? Okay. So anyone knows the high-speed, or you go to the dentist or something? Anyone knows where you use the high-speed motors?
Is that main drill you got?
The drill, right? Yeah. It's very high speed, maybe more than 10,000 RPM. So it's very fast, right?
Jet engines?
Jet engines. What is engine?
It's still spinning, right?
Okay, so here we have a motor, engine. What is an engine? Propeller.
Propeller, not engine.
Okay, that's a good question. So what is engine? Anyone has a difference between engine and motor? You have electric cars, right? If this car is complete electric, do you have engine? No, right? You have motors, right?
One's based on sex and one's internal combustion and one's.
Yes. So now you see the difference, right? If you have if you have both, then you need to have both, right? Engine it uses the gas, right? And motors use electricity. Okay, now this is a function generator. Again, later time when you study 110, 111 DC circuit, AC circuit, you are going to use a lot this in the labs. I don't believe you have been introduced this in this lab, in the labs here.
What is that?
Did TA show you this kind of a signal generator? Right? Not this, right? This one is a hard level for DC. So we do not use this one in our lab.
Just put a spoiler on.
And this function generator. So that means this equipment can give you some sinusoidal function like this, or can give you square wave, 5 volt 0, 5 volt 0, or 3 volt 0. So you can control this. And this one is a triangle. So up, down. So all are periodic signals.
When would you use a triangle?
Triangle.
Like, what would that be used for?
You can see this signal. That is a really good question. Anyone knows where to use this one?
No.
As far as I know, we only test this one in labs. For real life, that's a really good question. You tricked me. So in real life, we use these triangles. You can see the voltage linearly increases, then linearly decreases, drop. Right?
So it's not very efficient.
Is that like a dimmer switch on a light bulb, maybe? No.
How about this? Okay, you have at home you have the light bulb, right? Some are you can tilt the lights like this.
Like with the sliders? Or?
Yeah, if you slide, then this one, then the voltage will increase, lighter, brighter, then dimmer like this. So this one is maybe by application. Right? But this one you use manual to change this one. If you want to use automatically use this kind of signal, then you can see. You can imagine this on off, but in between is linearly increase or decrease.
Why does it all stay on the top side of the line, kind of like sine? Like sine goes all the way across, but then the triangle just stays on one side like a square.
You mean like this or like that?
He's talking about like why does sine go below the line and the square and the triangle does?
Which one? This one?
Yeah, so like sine goes all the way, like across the
Yeah, this one is the original signal that we generate from this alternator. So because we turn constant RPM, this always gives us this signal. They cannot give me this, cannot give us this. From this generator here, we can only, because this unit, when you turn this, you use constant speed, right?
Right.
And we can only get this signal. If you want this, you need to have a special circuit to convert this one into here.
Okay.
Usually you cannot directly generate this from this.
Why doesn't it cross the line then?
What line?
It just goes.
This one?
The horizon, like square and triangle don't cross the horizon.
Like why don't the square and triangle have negative values? Because it's switched.
You can have negative values.
Oh, it's just not on the picture, but
Yeah, but this one here, so for example, this is equal to 5, 0, 5, 0. If you imagine in real life, this is like on, you turn on, then turn off. Turn on, turn off. So 5, 0, 5, 0, right? You can move this down. So 5, negative 5, 5, negative 5, or even 5, negative 3, 5, negative 3. That doesn't matter. This one is the same thing.
Yeah, that was my question. I just, the way the picture made me think that.
Yeah, okay, that's a very good question. Actually, if you go to the lab later time for next semester, you can change this one. So you can, we are going to see the vertical controls. You can move this up, move this down, change this amplitude, change this amplitude. So you can see above the line, totally below the line, or you cross the line, or just like this on the line. So you can try this.
Makes sense now.
But all are rectangle. The shape is rectangle. This one, the shape is triangle. These are you choose which forms of wave do you want, right? So we have 3 sine waves, square waves, and triangles. And also you can choose control the frequency. The frequency is controlled by this one. So for example, if you push this button on the left, means the frequency is small. You can imagine if the frequency is small, it will be like this, right? If the frequency is large, it will be more like close to together, right?
Yeah.
Okay, so you control those different buttons. You can see very clear with the oscilloscope. Right? And also, you can adjust this, and those are the amplitude. This can solve your problem. You can make the positive or negative by this control. Right? The output level, sometimes you want the signal to be large, sometimes you want the signal to be small. Usually you want to start from small signal, avoid to destroy your device. Right? Then you can increase your level, but a good practice is do not start from a very high voltage. Right? So this one controls the output level, and the DC offset. That one is offset. If we have DC added to this, then this one will move up. Everything moves up. Like this one, you have a midterm score, right? Everybody get a score. I said give you a DC offset 10 points. Everybody gets 10 points up. So this one will be up. Right? Everybody minus 10 points. You don't like that, right? But okay, this one will be go down by, everyone will go down by 10. So that is called DC shift. Why is DC? Because it's constant 10. Right? Alright, so this button controls the DC offset. And if you change this one, you will see this waveforms will go up or go down.
So what's the difference between alternating and DC current then? Like sine is like alternating and the other ones are like DC because it's rotating, that's why it's alternating.
Wait, again, what's the difference? What's the difference between what?
Like sine is like alternating current because it's going on and off, like it hurts, but DC is because it's always on or always off.
Yeah.
Gotcha.
DC is always go one direction. AC opposite direction. Okay? If you want, for example, a real example, suppose we have a class here. Everybody go that way. No one turn around. So that is DC, right? If everybody just move left and right, but for a long time no one get out this side or no one go on get out that side, so that is AC. But if like 10 of you move to that side, but 3 of you move to this side, so in general, collectively, somebody will move like this way, right? But some part will like oscillating. So we have DC and AC in both components. Oscillating. Okay? So that DC is called DC offset. Right? Right? Duty cycle. Duty cycle is defined by the percentage that we have signal and the time that has signal with the total period. In this, usually duty cycle apply to square wave or triangle wave or something like that. In this case, this one is one cycle, right? And this part we have a signal, this one we have 0, so the duty cycle looks like 50%, right? So it looks like this one equals this, so it's 50% of the total. And this one duty cycle is equals 100%, because we have here, so the whole cycle has a signal. Sometimes we have this kind of triangle, right? This, up, then we have nothing, then up, down, we have nothing. So what is the period? The period is from here all the way to this point, right? So this is the period. And we have up, down, and level, up, down, and level. So in this case, the duty cycle will not be equals 100. And the duty cycle will be this one divided by this. We have buttons to control the duty cycle. And those 3 terminals are the output. And the readout, if you change anything in the frequency, the amplitude, then you can read the numbers from this screen. The sine wave, we know what is the amplitude in this example?
Amplitude.
right?
20, yeah.
What is the period? 50
microseconds.
We have other numbers. One is called the peak value. The peak value is the amplitude. So Vp for peak value in this case is also 20. So the peak value, what is for this one is 20. And Vpp is peak to peak. Right? The positive peak to the negative peak. So this Vpp will be equals to twice of Vp. So in this example, Vpp equals 40. Okay? And there are other important values called RMS value. Root mean square. Root mean square value is 0.707 times the peak value. Later time you are going to know why we use RMS value. What does that mean? Right? I can tell you briefly. The meaning is, for example, if you have a DC, like this, RMS value. If we have a sine wave like this, the amplitude equals 10. Suppose the amplitude equals 1. This is one cycle. If you apply this one, and we use the AC like this, then you apply it to a resistor. We know we are going to have power dissipated here, right? So this is one. Suppose this one equals the amplitude Vp, peak value, right? Equals 1. And I want to, instead of use the AC circuit, I want to use a DC like this. Voltage here, and use the same resistance. This one R, I use the same R here. What I want is, I want to generate the same power on the load. The same power. You can see this waveform is up, down, some zeros. This one is constant. So definitely, if this one, the amplitude constant 1, this is 1, they are not going to give us the same power, right? Because this constantly 1, this one is 1 maximum and sometimes 0 and sometimes value in between. So this one definitely gives us less power than this one. Does that make sense? If we use the amplitude here, right? Now the question is, what to choose the amplitude here to give us the same power on the same load? Right? That one is 0.707. Or, more accurate is square root of 2 divided by 2. Right? That is approximately equal to 0.7, like 70%. Right? So if this one, the peak value equals 1, then here we need to use 0.7 volt for DC, then they are going to give us the same power. How to get this? Right? You are going to use the method beyond the trigonometry. Right? Use the integral to find this one. But in this class, you only need to know the RMS value is close to 70%, 71% of the peak value. Right? Alright, example here, the peak to peak value is 40. The RMS value is for this example. If the AC peak is 1, it is 0.707. So it's 70% of the peak. So what is the RMS value here? 20 times 0.707, right? Make sense? So it's like 14.14, right? Okay, so 14.1. That means if you supply to the load with this AC power, the maximum equals 20, the minimum is negative 20 like this, you get some power on the load. Then if you use only a DC battery, 14.1, that will give us the same power. 14.1, what kind of battery is this? 14.1. How did you come here? You drive, right? Okay, the car battery usually is like 14. The rated is 12, but usually is 14. So 14, right? So if you use your car battery to supply to a load, to the light or something, then if you want to use it, instead use this, you want the AC, then this must be, the amplitude must be 20, give us the same power. Any question on this? Okay. For some purpose, the average value is used. The average value is not RMS value. The average. The average means the average of all this part. This one, do not consider this part here. It is 0.637. The actual value is 2 over pi, which equals 0.7. Again, we can use math to calculate this average value. You just do the integration, then divide it by the period, but we don't discuss here. The average equals 63%, 64%. The RMS value equals close to 71%. In this class, you need to know these numbers and the meaning, the physical meaning for this. What does this RMS mean? You don't need to know how to get that number. Okay, example here. The average value for this sinusoidal voltage is, what's the average for this signal? The average is like, suppose the average here, this is the high, this is low, you average like, at this point, make this one, make it the level, so average, right? You think this is the mountain, right? You want this, make this a flat, so you make it the level, so what is the height? That's the average. Right? What is the average? 10. The average equals 63.7% of the peak. Right? So that will be 0.637 times times 20, right? So it will be like 12.74, right? 12.7. Make sense? Everybody can do that, right?
Yeah.
All these things are very easy, but you need to pay attention, right? This will be in the test, so you need to be careful. Okay, now we are going to discuss some concept. What is sine wave? Anyone can tell?
Sine wave is
The amplitude period.
How to represent? With what function to represent the sine wave? Right? Sinusoidal function from math, right? How to generate this sinusoidal signals? Use the AC generator, right? Use this generator. We have a constant rotation of the shaft or something. Then we are going to have a sinusoidal output, current or voltage.
What's the difference between a sine wave inverter and a pure sine wave inverter?
Sine wave and
And a pure sine wave inverter.
pure. What?
Yeah, pure P-U-R-E, pure sine wave inverter.
P-U-R-E, pure.
Okay, pure sine wave means it's perfectly sinusoidal function. Right? When you said if you use a, right? Let me explain this.
Because I know like a microwave, for example, if you hook a microwave up to a sine wave inverter, it'll have issues, but if you hook it up to a pure sine wave inverter, it'll be fine.
You want to use this, right? This is sine wave. You said this one, right?
Right.
And there's another name. This pure is compared with anyone knows? Pseudo sine wave, right?
Okay, yeah, I've heard of that, yeah.
E-U-D-A-L, right?
How to write this? I forget. Anyone?
it's a DO, man.
SDO.
D-O at the end.
D-O, okay? Like that? Okay, pseudo sine wave.
D-O.
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 Oh, D-O, okay.
E-U-D-O.
You had it right, you just had to add a D-O.
You need
So
to,
P-S-E-U-D-O.
P-S-E-U-D-O. Okay, P-S-D-U-D. Like that?
E.
It's
E S U.
Okay, wait, only one. P-S-E-U-D-O,
Yeah.
right? Right? No? P-S-E-U-D-O, right? We have this kind of three concepts. This one, what is this? Mathematically, this one is this.
Yes.
Right? When you emphasize pure, this is compared to this one.
Okay.
Right? Sine wave is just like a perfect sinusoidal function. So this one is this, mathematics.
Okay.
Why this sometimes like this? It will be like this generated from a square wave. The square wave is like this, right?
Okay.
But you may want to have something like this.
Oh, so that it never actually turns off all the way?
No, the perfect sine wave will be like this. But this one looks like a sine wave, but maybe flatter on the top.
Okay.
Like this.
Okay.
You can see it's still sine wave, right? But it's not perfect.
Right.
It looks like sine waves, but looks like a square wave also.
Okay.
So this is called a pseudo sine wave. Right? If a product said, okay, emphasis, we have a pure sine wave, that means it's this one. Just to distinguish with this one. Means the quality is better in sine wave.
So I guess that would be the reason, like if you hook a microwave up to a pseudo sine wave.
For microwave, I believe you can use any. This one doesn't matter. But only sometimes a computer, sometimes some equipment you may want high quality sine wave. Right? But a lot of equipment, for example, if you want to heat your home, right? In the winter you want to drive your home, you can use any of this. Doesn't matter.
Okay, well, so I was wondering because like I've been trying to look into like solar panels and making off-grid solar system. And in the inverter side, they had different kinds of inverters. They said you always needed to use a pure sine wave inverter, but I didn't know what that actually meant. Like
because in the solar
I
panel,
wanted to use it.
in the solar panel, the output is DC. Right? And our home appliance cannot use DC directly. We need to use AC. And this one theoretically supposed to be a pure sine wave. It's perfect, right? It's generated from the generator, so supposed to be perfect. But if you have a DC, use the inverter. If the quality is not bad, it's very cheap, then they usually give you this kind of sine wave. It's called pseudo sine wave. Right? But if you use this pseudo sine wave to drive your light bulb, still works. But to drive something others, you may have a problem. So that's why some products say, okay, my output is a pure sine wave. So that means you can use it as this kind of power. So definitely, if this is true, then they are going to sell you for high price.
Yeah.
And definitely you need
They
to
charge more, but
charge more.
I just
Yeah.
didn't know what the difference was, and I was looking at
The difference is
trying to
only
find out.
some kind of equipment only works for better quality sine wave.
Okay.
But most of them don't care too much. Right? So depending on what your application is, you want to spend this more money. How much do you want to charge more?
Right.
And what your application, right? Okay, that's a good question, right? AC current. AC current not necessarily sine wave. Can be like any, like what is AC? Alternating direction, right? So you just back and forth, have positive, negative, and that is AC current. But we are going to start at the beginning with just sine wave because that is fundamental. Period, we know that, right? Yeah. Okay. And frequency. Yeah. And how many periods are in 1 second? How are these two related? F times T equal to 1. Hertz. What is Hertz?
It's the unit.
That's the unit for
Time.
time. For frequency.
Frequency.
Okay. So Hertz is the unit for frequency.
Yes.
Frequencies based off time. So.
Yeah, time is per seconds. Seconds is per time. Frequency is just occurrence is per second.
So Hertz is 1 over 1 second.
Yeah.
Right? Hertz is 1 over 1 second.
Yeah.
instantaneous value. Now,
Is that like on and off?
no, instantaneous value means that's the value at that
Yeah,
time.
the value of one like instant, like.
At that instant.
Yeah.
As the instant we are interested in. For example, here, for sine waves,
Like at 25 microseconds, what is the value?
for example, if a voltage change with respect to time as like 10 times the sine, for example, 377 t, right? That's the sine wave. If I draw this, it will look like here. So the peak equals 10. This one is negative 10 here. I ask you, what is the value when t equals here? That means what's the value at this point? Right? That is called instantaneous. That means the value at this time instant. That makes sense? I'm not asking the peak. I'm not asking this negative. I ask what is the value at this time instant. That's called instantaneous value. Questions? That's easy to calculate, right? Because for example, I ask this t, when t equals 0.1 millisecond, what is the instantaneous voltage when t equals 0.1 second? You just plug this one into here, then calculate the sine wave, then multiply by 10, then you get the value. That will be at this value. Does that make sense? So that t. I believe the textbook will discuss this concept, right? Peak value, we know that, right?
Yeah.
The maximum or the negative maximum. Peak to peak,
Yeah.
y is the peak, from the very top to the very bottom. And RMS value, how to understand this? What is it?
RMS.
Okay, we have two problems to think. The first one, how to calculate the RMS value from the peak. In this one example, the peak equals 10. So what is the RMS value? 7.07, right?
70%.
Okay, so that is how we calculate it. What's the meaning of this 7.07?
Oh, AC.
Okay, if you apply to a load, for example, to the light bulb or anything, with this AC current, the maximum equals, the peak equals 10, okay, you generate a power on the load.
Yeah.
Now you change your mind, you want to change to a DC source. But you still have the same power. So that DC source, the voltage need to be like 7.07, smaller than 10, right? Only 70%. So that is called RMS value.
Everything only goes on your software documents.
RMS value is called
Root mean square.
root mean square. Root mean square. Radius. What is this? If you know trigonometry,
That's part of your revolution value.
yeah, the radius compared to degrees, right?
Yeah, degree.
How degrees and radians are related? For example, 180 degrees equals how many radians?
Two radians.
180 is just pi.
180 equals pi, right?
Yeah.
So one term, 360 equals 2 pi. Right?
Yeah.
So they are linearly related, but you can, so give you, for example, pi over 3 radians equal,
I can't remember all that.
how many degrees is this?
It's like 1.5 rotations.
Pi over 3 radians,
It's like, that's like one.
60.
60 degrees, right?
Yeah.
Okay, so we need to convert this back and forth quickly. Phase, what is the phase? Mathematically, phase is only the angle. Yeah? Sine something, 30 degrees, so that is the angle. But in electrical engineering, that part is the phase.
Oh, your times?
377 times time.
Yeah.
So everything after this sine function In math, we said this is sine, okay, 60 degrees.
Yeah.
That is the angle, right? And this one here, this one, in radians or in angles, degrees, no matter what, this is called the phase.
Yeah.
The phase actually is relative. It's relative to a reference. Amplitude, that's
Yeah.
maximum value, right? And the pulse, a type of waveform that consists of two equal and opposite steps in voltage or current separated by a time interval. Is this a square wave? I think you are interested in this, right? You brought a very good question about this square wave. So this is pulses. What pulses? Pulses will be like this is a type of waveform that consists of two equal and opposite steps in voltage or current separated by a time interval.
So that's what happened with that pseudo thing is,
This is just a square wave. For example, positive 5 and negative 5,
Right.
positive 5 and negative 5.
right.
Eh? So these are the
So a square uses.
square waves. Harmonics. Harmonic.
I don't know what that is.
Harmonic is a sine wave or cosine wave. Right? But when we discuss harmonics, usually we have a more meaning for this.
Yeah.
It will be multiples of your fundamental sine or cosine waves. What does that mean? What is the frequency on this wall? 60 hertz. Right? But if you use this one, for example, for your appliance or your radio, you use this. We do not consider the battery. We suppose we use this one. Right? And in the circuit, sometimes you are going to have a harmonic noise. Right? We know the input has only 60 hertz, but sometimes you have 120 hertz. That is twice of this one, right?
Like coal mine in a video car.
Radio.
You blew his mind before.
Well, what's it like, if you take, for example, if you take a video card for a computer, you take all the fan and stuff off and you run power through it, and you listen, there's a noise.
Yes, that is called the hum
Yeah,
or
that-
something.
that-
That noise.
That's harmonics.
Yeah.
That is the 120 hertz.
Yeah.
And sometimes even you have 180 hertz noise. That is the second harmonic. That's the third harmonic. 3 times of the fundamental. So this 60 hertz is called fundamental frequency. And 120 is the second order harmonic. 180 is the third order. Then 240 is the fourth order. The bad news is we have all these harmonics all up to infinity. The good news is the amplitude or the strength will be much smaller for high orders. So that's why you're only aware of the 120. You're seldomly aware of the 180, let alone 240 or even higher.
Okay.
Eh? So you may wonder why we have this harmonic noise, because your design, not your design, the design is not perfect. Right? You have a non-linear device inside. For example, you have a diode inside, then you are going to definitely get a second order harmonic 120. So sometimes if this is very serious, but your application need only the fundamental, then you are going to use a filter.
Is that what we're hearing right now?
No, that's all.
This
No,
like,
that's that fan about to go out.
This is the introduction. So this,
You talking about Ellison, man.
right?
I mean, there's like a noise in the background, like
Here?
It's the projector the fan's trying to.
Yeah, sometimes it is, sometimes it's not. Okay, it depends. Right? Not all of them are.
I was deaf to it too.
Because like-
Okay, now we have a quiz for this. I've been using it for a time. I wish I was.
Dang, bro, why bring it up?
Okay, again, this slide is only summary, so not all of the topics in the textbook have been discussed here, but the questions may ask this question. So at this time, we are going to explain a little bit more. Okay? The first one, in North America, the frequency of the utility voltage here is 60 hertz. Keep this in mind. If you are in EET, you are going to take all my higher level courses. I keep asking this, so don't forget. If you forget this, I will be disappointed. 60 hertz. What is the period?
Hold up.
Oh.
It's gonna be,
B.
because it's 20.
F and T are related by 8, right? Okay, F times T equals 1. So the period equals 1 over 60,
B.
which is B, 1 over 60
C, that's, no.
C.
C.
is B.
No, it's B.
No, you got 1 over 6.
1 over 6.
Yeah.
Equals B, right?
Yeah.
Yeah.
Yes? Right, 1 60, right? That's B.
Tripping, bro.
Okay, next one. The amplitude of a sine wave is measured at the maximum point between the minimum and maximum at the midpoint anywhere on the wave.
The amplitude of the sine wave.
I'll give you a sine wave like that.
Maximum.
I ask you what is the
Max.
amplitude?
8.
Maximum.
8. Max.
8, okay, at the maximum point. That is. It's too easy, right? Alright, next one. This one is a little bit.
Example of an equation for
An example of an equation for a wave that lags the reference.
what does it mean like?
Okay, that means we are talking about the phase. Right? The phase is when you how you start. Okay, today we have rain, right? Okay, somebody come here late.
C.
Suppose 9:45 is the reference. If you 5 minutes late, you are -5.
Oh,
That
this
is called the
this
reference. Lag is the reference.
This is.
What lags the reference? Which one? C, right? Okay, perfect. So data, here data we use as the reference. If you have data -27, then that is lags the reference. That make sense?
Yeah.
Which one lag the opposite is called the lead, right? L-E-A-D.
Oh, the lead.
Which one lead? That's one.
B.
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 Lead
right?
means add.
Wait, lag.
Is earlier than
You're
that,
right,
right?
You're right,
35 minutes early.
What is D?
D is just.
It's not a function.
It's not a function, it is a function, it's a constant.
D is O.
That just means
Yeah, it just means one direction. So what signal we call that? Yeah, what we call it? In this class today we discuss AC source, AC voltage with AC current. What is D?
Direct.
Direct. It's called DC, right? How about A?
A is frequency.
A is a little bit beyond our level in this here, right? So actually A is 180 lag or lead. It's the same thing, right? Okay, so we don't discuss A. Right?
Like, would you ever have like 12 volt AC current?
Tell where AC current, yeah.
What would that be used for?
Just AC current. If you generate that one, it's just AC. But you're, for example, you want to rectify it into DC sometimes. You can use AC to drive your light. Our light, all our light at home, I cannot see all, but most of them use AC.
Right.
See?
No, I was just wondering because we've always heard it, like you were just talking to people and you said like it's 12 volt, but automatically assumed it was DC.
Because that is for car battery, so everyone knows that.
Right,
That's right.
right, that's-
But can be AC.
Yeah, that's what I was wondering. I was wondering if there was any reason it couldn't be, but you said it can, so.
For example, if you want to make a charger can only use DC. So you want to use this wall to charge your, for example, your something like a radio or something. You need to rectify this AC current voltage into a DC voltage. Right? But this one is too high because this is equals 120. If you directly rectify this one, the output voltage will be equals more than 170 something. It will destroy your device. So you need to use a transformer to reduce the voltage to, for example, 12. Right? That's your 12.
So like a solar panel itself
That is
is a
DC.
DC.
Yeah.
It's a source, so it's a DC.
Yeah. Okay, next one. In the equation, this the letter V stands for. Which one?
C.
D. D. Who says D? Who says D?
I think it's B.
I'm asking who says D? Anyone? Good. Stand up to yourself. Wait, D is correct, right? D is the instantaneous value.
Thank you too much.
Right? The peak value is VP. The average value is what is the average value? 0.7. Oh, that is RMS.
Oh, no, 6 point something.
0.637. Right? The time base for oscilloscope. That is the equipment, very, very important. You're going to use this a lot of time. The time, the oscilloscope, I can draw the screen. The oscilloscope. And oscilloscope, we have some control somewhere, right? And this is the screen. You're like this. This is T. This is the voltage or current. For example, if we observe a sinusoid function, it looks like that screen is too small. Like this. Like this. Okay, that's T. We have some buttons or somewhere. Okay, you can control it.
B.
The time base for oscilloscope is determined by the settings of horizontal. Yes, you control this horizontal, right? This is horizontal. And if you want to control this one, it's called vertical control. Control the amplitude. Okay, good. A sawtooth wheel. An equal positive negative going ramp. Two ramps, one much longer than the other. Two equal positive, two unequal positive.
B.
We didn't discuss this in the slide, right? But we know C and D, two equal pulses is a rectangle wave, right? Two unequal pulses also rectangle wave. So we have only A and B to guess. A is equal positive and negative going ramp. This, what do we call that?
The triangle.
Triangle, right? Then B. So B, right? Two ramps, one much longer than the other. Like this, then down, then up, down. So this is still like triangle, but it's not.
It's not perfect triangle. It's like,
I just thought about the
it's like
name.
obtuse triangle.
What a sawtooth look like?
So sawtooth actually is, you know the saw, right?
Yeah.
So one is longer, one is longer, one is shorter. It's still a triangle, right?
Yeah.
Let's go, bro.
I don't think this question is very good, but the number of readings in 90 degrees is
Power two.
pi over 2. Okay, perfect, very quick, right? So pi equals 180. Yeah. You keep this in mind, then you know this. For the waves shown, the same power would be delivered to a load of a DC voltage is, don't
D.
tell, okay? Everybody think this. This is important.
D.
Everybody think this, keep to yourself, then I will ask.
I feel like it's the highest point.
First, I will try to understand the question, right? Same power, we mentioned this a lot of time, right? Same power for AC and DC. What we are talking about? 3 letters. What is it? RMS.
C.
C.
Yeah.
Yes.
Yes.
Yeah.
Anyone else? If you multiple choice, this one you don't even need to use a calculator, right? You see, all these answers are separated by a large gap. So you just 70%, right?
Yeah.
70% times 60, 42 something. There's only one, 42, close to 42. So C. Okay?
Hey, how did you get that?
Question on it? Everybody needs to know this. If not, you are going to be in trouble.
How you
A square wave consists of fundamentals and all harmonics. Fundamentals and even harmonics. Fundamentals and all harmonics, only the fundamentals. Right, so here we need a little bit of explanation.
C.
Okay? Square wave, again, this
it's equal.
Square wave like this. Suppose we know the fundamental frequency is like a, you said pseudo waves, right? Pseudo sine waves. Right? This frequency, the sine wave, gives us the fundamental frequency. Okay, so now you said this square wave has only the sine wave here. Definitely not, right? We have more information here. So we said only the fundamental, wrong. Definitely wrong. Right? Fundamental means we have only this sine wave here. And this is not a square wave. Right? And we have fundamentals of all harmonics. C is not correct.
Oh.
And you need to read the textbook a little bit more. Right? The answer, I believe, that is A.
Hey.
Oh. The harmonic means the first, all the harmonic means the first, the third, the fifth, the seventh. Even harmonic means the second, the fourth, the sixth, the eighth also. So read the textbook to find this. Right?
What's the thing?
A control on the oscilloscope that is used to set desired number of cycles of a wave on the display is. Let me explain a little bit this. Division, because on the screen of the oscilloscope, right? So this is the screen of the oscilloscope, and there are two middle lines here, and we are going to have some vertical lines. All these are called divisions. So this will be horizontal divisions and vertical divisions. Divisions means this. Right? If we want to set the desired number of cycles of a wave on the, right? So we need to set volt per division or time per division, trig level control, horizontal position. Right? The trig means if you have a signal applied to this, there are two terminals here somewhere, it's called probe. I mean right here, right? For the camera to see. Probe, right? You apply this one. Usually, if you do not have the trig, the trigger is just like started to show on this oscilloscope. So suppose the signal looks like this. The horizontal position control is you can move the whole thing to the right or to the left. Right? That's the position. So here, here, here. So that is the position level control. But you do not change the shape. You do not change the frequency large or frequency small or the amplitude large or the amplitude small. You do not change anything. You only change the position. Move to left to the right. So that is called horizontal position control. Or there's another one is called vertical control. You move the whole thing up and down. Do not change anything else. Time per division control. Right? This is time per division means, for example, 50 microseconds each division. So if you know this is 0, this is 50, 100, then you can measure the period. From the period, you know the frequency. Right? So that is called time per division. And the voltage per division means this way. So this is a volt per division, and this is time per division. Means for each division, for example, equals 5 volts, equals 10 volts, or equals 0.1, depends on how large your signal is. Can be large, can be small. Right? So now tell me which one. You want to change the desired number of cycles of the wave. For example, you want to see more cycles. Right? You can see only 1, 2 cycles on the whole screen. Or you want to see a lot of cycles. Or you want to see 1 cycle to make it like a zoomed in or zoomed out. So which one you want to change? Time per division, right? So change the horizontal. There's a knob here. You change this one, it will be this and this, right? Again, later time you go to the lab, not in this class, you are going to play with the oscilloscope. It's very useful equipment. Everybody needs to know that. I believe that's it. Okay, thank you.
Where do you want the homework?